Horizontal asymptotes. What is a horizontal asymptote? A horizontal asymptote is a horizontal imaginary line. It's a dashed line that we draw when we're starting to sketch rational functions to let us know where our graph will, what my graph will approach, what y value. Okay, it's basically studying the end behavior. And you've heard this word before when we did polynomial functions. And let's say I have a horizontal asymptote here. Horizontal asymptote, let's say it crosses the y-axis at that value, okay? And what this helps us with is knowing what the end behavior of the function, what the end value of the function will approach. And what we do is we figure that out from our original function, but I just wanted to show you what this looks like in a graph. It's not part of the graph, it's just a guide for us to be able to draw the graph. The same with vertical asymptote. They're just guides that help us sketch the graph. They are not part of the graph. Okay, so let's say this is my horizontal asymptote. I don't know what value my function will approach, but let's say it approaches this value, whatever it is, and this is what it looks like. When my value for x moves away very, very far from 0 this way, the farther I get from 0, the closer my function will be to that horizontal asymptote. And it gets closer and closer, infinitely closer. Sometimes the graph will cross or touch the horizontal asymptote. That is okay. Most of the times it doesn't. It never touches it or crosses it. But you will see some functions that will approach it, cross it, and still approach that value. But if it was approaching it from the top of the horizontal asymptote, it crosses it, now it approaches it from the bottom. But it basically stays very close to the horizontal asymptote. And if I were coming this way, maybe it could look like this. The farther I get from 0 on my negative x-axis, the closer my function will be, sorry about that, to the horizontal asymptote, okay? So that's what it is. That's what a horizontal asymptote is. It's a line, it's a horizontal line, and when x values are very far from 0, it tells me what value the function approaches. When I have a function written in this form to determine where the horizontal asymptote is, I'm going to concentrate on the leading terms. If my polynomials in the numerator and denominator are written in standard form, like these are here, I will concentrate on the leading terms. Because remember, we're under the assumption that x is very far from 0, so that means this value is very, very, very large. So if I think about a very large value, let's say x is 1 million, and I take 1 million and I square it. That's a very big number, and then I multiply that by 3. That number is so big in comparison to these two, that these are practically non-existent. Here's what I mean. If I have a million, let's say I have 1 million plus 0.5. That's 1 million, 0.5. 0.5 is so small in comparison to 1 million that I can say that this is equal to 1 million, right? Approximately 1 million. That's what it means. This value is so small, it's practically, you could depreciate it. It's practically non-existent, okay? So the same thing happens here. When I have 3x squared and x is so and so large, when I add or subtract this little bit, this will practically be the same, okay? And the same thing happens down here. Imagine 1 million cubed. 1 million cubed and then multiplied by 2. And then I'm coming and adding this little bit of 5. That's just basically equal to this number, okay? Plus peanuts. So I can just eliminate the 5 and not add it at all because it doesn't change my value that much. So that's why we concentrate only on the leading term. So I can say that this is approximately equal to 3x squared over 2x cubed, right? Because these are so big, and this is when x is very large. Okay, remember this is not what we do for the function. It's just when x values are very far from 0. I can say that this will be equal to that. And when I do this, I can now evaluate or think, what would this value approach? What is this approximately equal to? And I'm going to teach you by using an example with M&Ms. 3x squared and 2x cubed. If I were to substitute an x for these values, let's say x is 1,000,000, I would have 1,000,000 squared in the numerator and 1,000,000 cubed. Which of these two would be the largest number? The largest number would appear in the denominator. And believe me, 1,000,000 cubed is much, 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 much larger than 1,000,000 squared. So this is like having, let's say I have one M&M. Let's say I have one M&M over 1,000,000. This is just an example for you to understand what I'm trying to get at. If I have 1 divided by 1,000,000, that means if I have one M&M and I have to divide it into 1,000,000 people, I have to divide it amongst 1,000,000 people. How many pieces, or how much of the M&M will each person get? 1,000,000 people, you have one piece of M&M. How much? Or what piece of an M&M would each person get? They would get very little, right? Each person would get such a small piece. I think it would be microscopic if you tried to break a little M&M into 1,000,000 pieces so that you could give each person one little piece. That piece would be very microscopic. So when you say that in numerical terms, you could say, well, if each person got a little bit of that one M&M, that's equivalent to having nothing. You got nothing. It's so small. You lose it, right? You can't see it in your hand. You can't find it in your hand. So this is basically 0 when you have a small number over a big number, a very big number. That will approach 0. So whenever you have a small number over a big number, this horizontal asymptote, the horizontal asymptote will be your x-axis, which is your y equals 0 x-axis. Okay, because this approaches a value of 0, so y approaches 0 when we're thinking about very large x values, and that becomes your horizontal asymptote. When I have a function where, for example, I have 4x to the 5th power minus 3x squared plus 6x minus 5 divided by 3x to the 5th power minus 5x cubed minus 6x squared plus 4. Notice here that if I want to find my horizontal asymptote, I concentrate again on the leading terms because they're so big, these x values are so large that it makes these other additions and subtractions practically nothing compared to the enormity of these two numbers. Okay, so this is practically 4x to the 5th power over 3x to the 5th power. If x is very large, remember, very, very large, 1,000,000 to the 5th power, 1,000,000 to the 5th power. In this case, since I have the same degree in both numerator and denominator, I can say this approaches 4 over 3 because I can cancel these two out. So this will be my horizontal asymptote. This will be the value that my function approaches when x is very large. Okay, that's what happens. When x is very large and the degree in the numerator is less than the degree in the denominator, I basically have a very small number over a very big number, and that always approaches 0, because remember, each person will get such a small piece of the M&M. It's microscopic. It's like having nothing. It's 0. And when that happens, that means when I have very big values, the function will approach the y equals 0 value. It will approach 0 when this happens. So that means I have a horizontal asymptote at 0. Okay, so in summary, this is what we're going to do. In summary, how do I find the horizontal asymptote? This is what you need to learn. I'm gonna write a polynomial here, and let's say this is a x to the n over b x to the d plus some other terms plus some other terms. Whenever the degree in the numerator is less than the degree in the denominator, like what happened in our first case, the degree in the numerator is less than the degree in the denominator. So whenever n is less than m, n, remember, is the degree in the numerator, and I said m here and it should be d. This is d. Whenever n is less than d, and d is the degree in the denominator, that's why I use d for denominator. Whenever n is less than d, then I will have a horizontal asymptote in my graph. Asymptote at y equals 0. And this is the same thing as the x-axis. Whenever n is equal to d, that means whenever the degree of the numerator is equal to the degree of the denominator, like we had here, the horizontal asymptote, or the graph, will approach the horizontal asymptote at a over b. A over b means the coefficient of the leading term, or the leading coefficient. A would be the leading coefficient for the numerator. B would be the leading coefficient for the denominator. So a over b, because these two would cancel out if the exponents were equal. And we're only looking at the leading term because that's the values that are so big. The rest of it doesn't matter. So that would be my vertical asymptote would be y is equal to a over b. Okay, and now I'm going to give you some examples. On the next video, we're going to determine the horizontal asymptotes and different functions so that we can practice this. This is just a demonstration of how, well, where this comes from. How do I find the horizontal asymptote and what the analysis behind it is. Okay, I hope you understood. If not, watch the next video and I'll have some straightforward examples on it. Okay, but these rules you have to remember. When n is less than d, the horizontal asymptote is at y equals 0. When it's equal, the degrees are equal, then it's going to be y equal a over b, which are the coefficients of the leading terms. And if you're asking what happens when n is greater than d, when n is greater than d, there is no horizontal asymptote. We get a slant asymptote. And a slant asymptote, we need to do long division and find a quotient, and we graph the quotient. Okay, for now we're only going to do n less than d and n equal to d. And we're only going to work with those two asymptotes. Okay? When n is greater than d, we're going to say no horizontal asymptotes. I'll see you in the next video.